Hello, hello, we are live. Perfect. Okay, welcome in this live stream. It's going to be the first of a long series of live streaming on scuba equipment, and we have a really special guest that is a real big expert of scuba diving equipment. And just before to introduce him, just few things about this live stream. The live stream is live on both Facebook and YouTube. You can ask whatever you want on scuba diving equipment, of course, and other things. Nothing more. It's going to be not a really long live stream. So think already about your question, and if you want, just leave a comment, and we are gonna ask. We are gonna answer. I leave you with Steve.
Great, thanks. Thanks, Andrea. Hi, everyone. Good evening to all the people that are in good locations, particularly you guys at Takatia who are on an island. I can hear the crickets in the background. I wish I was there. It's nice and cold in Johannesburg. My name is Steve Rusznyak. I am the general manager of Scubapro for Sub-Saharan Africa, which includes the islands as well. And Andrea has asked me just to do a little presentation on scuba equipment, and starting really from a very basic level, looking at hard gear and what a scuba set actually makes up. So I'd like to just move on to the share screen, if that's possible. Andrea? Sorry, the share screen is there, yeah? Okay, everyone's seeing that? Great, so welcome. The one thing that I must just say is that this is a general equipment. It's not based on Scubapro equipment specifically, but obviously with me being the general manager of Scubapro in Sub-Saharan Africa, this is the equipment that I've been working with for the last 30 years in the diving industry. So yes, I will try my very best not to be biased around this equipment. Alrighty, so just moving into a little bit of the history around Scubapro. We were established in 1963. We were the inventors of the piston regulator, jet fins, which were a René Bouchard design that Scubapro bought patent for and then manufactured. We invented a decometer, we invented the BCD, we invented the power inflator, the standard piston design regulator, and the balanced piston design regulator. So as I say, I'll try to remain unbiased just with respect to that, but we've got quite a proud heritage in terms of diving equipment. But Andrea wanted to try and make this a little bit more general in terms of the information that is out there. So the first thing is to start off with, what is a scuba set? Well, that's quite easy when we're talking about hard gear. You'll hear instructors talking about hard gear and soft gear. A scuba set is basically made up of three major components. We're just waiting for the slide to change there. Okay, so a scuba set is made up of a demand valve. You will sometimes hear this referred to as a reg or a DV. DV stands for demand valve. And generally, this is the first stage with the second stage. It includes usually an SPG, sometimes a depth gauge, sometimes with a compass. You will have your octa or alternate air source on there, and you'll have your low pressure inflator hose. You might, if you're in cold environments like Joburg at the moment, be diving on a dry suit, and your inflator hose for your dry suit would be connected to the demand valve or the regulator. The scuba set is also made up of the BCD, or the buoyancy compensating device, or called BC for short. And the BCD is obviously what allows us to control our buoyancy, both negative, positive, and neutral buoyancy, to make us feel like poor man astronauts underwater with the neutral buoyancy. And this is connected to the regulator or demand valve via a low pressure inflator hose, and that then connects through to the cylinder. Okay, and the cylinder is actually then the third and final part of the scuba set. Generally, these days, we are using 232 bar cylinders. Mostly these are pumped to 200 bar. Some of you might still have some 300 bar cylinders. 300 bar cylinders were very, very common in the sort of 70s, 80s, and moving into the early 90s, primarily for technical divers. But the reality is that mostly on the technical diving, and I'm a cave and Trimex qualified diver myself, in a cave, we generally don't want to use 300 bar because if you've had any failure on a hose bursting, if it is at 300 bar, you'll lose a much larger volume of gas. So we tend to find these days that most cylinders are 232 bar or pumped to 200 bar. Okay, so that basically is what makes up the Scuba Set. And let's just look at what the regulator physically does. So if we are talking about 300 bar potentially in a cylinder, which then will range down to what we consider as a low on air or 50 bar, that obviously is what we refer to as high pressure in the diving industry. The job of the first stage of your regulator is to reduce this high cylinder pressure to what we refer to as an interstage or intermediate pressure. The reason why we refer to this as the interstage pressure is it is the pressure that the first stage reduces the high tank pressure down to, and this is generally at around 10 bar. For all Scubapro regulators, we operate on 9.5 bar of interstage, but different manufacturers will operate on different interstage pressures. For the purposes of tonight, we are going to refer to interstage pressure at around 10 bar as an average to try and incorporate all brands of equipment. But this can run from 8 bar up to 13 bar in some brands and models within those brands. So the first stage reduces that high tank pressure down to the interstage pressure. The interstage pressure is the pressure that is then actually sitting right at your second stage. So the moment you are taking a breath from your second stage, the job of the second stage is then to reduce that intermediate pressure or interstage pressure down to ambient pressure. So I'm hoping that everyone understands. Let's see if your physics is good. But if we are at 30 meters, ambient pressure is there 4 bar. Okay, if we're at 50 meters, ambient pressure is 6 bar. So the job of the second stage is to reduce that interstage pressure down to ambient pressure. Alrighty, so just having a quick look at evaluating regulators, and I know that this is quite difficult for customers. They walk into a shop and they see a number of different brands and different models of regulators, different colors and different designs. But what we're wanting to ask as a question today is, what makes a great regulator? Excuse me. Obviously, the first thing is performance. So we should be looking at breathing characteristics of the regulator. We're going to look at this now. But this is not only the most important thing. The performance is very important, but important as well are the ergonomics. So in other words, the comfort characteristics. You'll be amazed on certain brands of regulator where, for example, they use a big mouthpiece. You find customers coming up after dive saying, "Oh, I really hate that regulator." And you ask them afterwards and say, "But why did you hate the regulator?" And it's, "Oh, the mouthpiece is uncomfortable." So that would fall into what we refer to as ergonomics. That is basically the streamlining of the entire regulator, how comfortably it sits in your mouth. Is there a lot of weight in terms of the regulator? So you feel like you are having to really clamp the regulator with your mouth, and maybe your jaw muscles are getting tired as a result of that. All of those particular characteristics, and in fact it can also incorporate things as simple as the hose itself. So for example, some manufacturers use very thick hoses, which are exceptional for performance. They allow good airflow through to the regulator, but because the hose is thick, the hose is also very heavy. And you're holding that, obviously, with your jaw muscles in the regulator with the weight of the hose. And then when we start to look at quality, we also must look at the quality. So we talk about QDR, or quality, durability, and reliability characteristics of regulators. And we feel that these are 3 very, very important things to look at. So it's not just about comfort, it's not just about color, it's not just about performance, and it's not just about quality. All 3 of those are very important. Okay, so let's have a quick look at the breathing characteristics. Okay, with respect to breathing characteristics, what we should be looking at on regulators is a very low inhalation resistance. So in other words, when we are taking the first sip of air from the regulator, we should, sorry, Andrea? Sorry, Andrea, I can just hear you in the background there. Can I ask you to, yeah. Thank you. Can I ask you just to mute your mic there? Sorry, it's a bit distracting. I can hear it in my ear.
Sorry, Steve.
Okay, let's get back to, okay, we're seeing the screen there. Okay, so just in terms of low inhalation resistance is the amount of energy that we are expending just before we get the first sip of air or the first atom of gas from the regulator. This inhalation resistance should be very, very low. And in fact, this resistance should be very low throughout the inhalation cycle as you're breathing in. We should also have low exhalation resistance. So in other words, in order to clear out the unmetabolized O2 and any of the carbon dioxide that we are breathing out of the regulator, there should be a very low exhalation resistance. So in other words, we should not be expending a lot of energy trying to get our unmetabolized oxygen and carbon dioxide out of the regulator. And then obviously, very important is high airflow from regulators. So for example, there, we start talking about Scubapro regulators, and we have the highest performing regulators in the world from a flow rate point of view. When we look at something like our Mark 25 EVO regulator, it can supply over 10,000 liters of air in a minute, which is the highest performing first stage valve on the market at the moment. And you might be asking yourself the question, why does that first stage need to supply 10,000 liters worth of flow? And in fact, it's, as our engineers say, 10,000 liters in 1 minute is more than 4 stressed elephants could breathe at 100 meters of depth. Okay, as a human being, you couldn't breathe 10,000 liters in a minute, it would kill you. So why are manufacturers chasing flow rates with respect to the performance on the regulators? And the answer to that is quite complicated, but I would like to try and simplify it for you. Generally, this is as a result of interstage pressure. So remember when I was saying that the first stage of the regulator combination, the job of that first stage is to reduce the high tank pressure down to the intermediate pressure. And we said on average, depending on the manufacturer, at about 10 bar of interstage pressure. Depending on the flow of the first stage through the regulator, as well as the second stage, this will control how quickly the interstage pressure recovers back up to 10 bar. So if, for example, you have a low flowing regulator and you put an intermediate pressure gauge or an interstage pressure gauge onto the regulator to look at the interstage pressure, the diver takes a breath off the regulator, the interstage pressure, let's say on a poorly flowing regulator, drops down to 2 or 3 bar, and by the time you're wanting to take your next breath, the interstage pressure has not actually recovered back up to 10 bar of interstage pressure. So the reason why we are chasing high flow rates is not that you're going to breathe 10,000 liters of air or gas in a minute, but this is so that we can limit the interstage pressure drop. We call this dynamic variation, and basically dynamic variation is directly related to flow on the first stage. So the higher the flow on the first stage, the lower your dynamic variation, or the lower the interstage pressure drop. So in other words, on something like a Mark 25, if you put that onto an interstage pressure gauge, you will see that the needle just flickers. It drops very, very slowly and then recovers right back up to 10 bar, or in the case of Scubapro, 9.5 bar of interstage pressure. So in other words, the airflow is there, ready and waiting for the diver to be able to breathe from the second stage. And then the last important thing in terms of breathing characteristics is also that you have progressive air delivery. So in other words, we do refer to this as a demand valve. A demand valve should be giving you gas on demand as you require it. So progressive air delivery means that as you are breathing in nice and gently on a typical dive in Madagascar at Sakatia Lodge, nice visibility, very, very warm water, you're nice and calm, and you are just very, very smoothly breathing from the regulator. There should be no restrictions in your inhalation, and the regulator should give you the gas that you require as you require it. This also becomes very, very important in stressed situations, and also it starts to become important at deeper depths as well. So if, For example, you have to swim into a current, you might be requiring more from your regulator, and the regulator should be able to give that progressive air delivery and high airflow to you on demand as you require that gas. Okay, looking at the comfort characteristics, you'll notice that most manufacturers have now moved away from metal second stages. Metal second stages were very, very common in the 60s, 70s, 60s, 70s, and 80s, even into the early 90s. Generally, those were very, very heavy, which meant that divers were expending quite a lot of energy keeping the regulator in their mouth. Technology has got a lot better, so you will see some metal second stages out on the market today. But the technology in terms of manufacturer has got a lot better. So what I like to say is, we've got to understand that with regulators from a physics point of view and design point of view, and the way that they operate is not very different to what Gagnon and Cousteau designed in 58, 59, and Scubapro invented with the piston regulator in 1963. The physics is very much the same, but guys, it's very much the same as combustion engines or motor cars. So we've been making motor cars for well over 100 years now. I can tell you that we are doing a much better job today than we were doing 100 years ago in terms of performance, efficiency, etc. Okay, so lightweight does become a very important feature, and technology actually allows us to make the metal second stages quite thin, quite lightweight, and there are some benefits with respect to that lightweight. As I said, you have no jaw fatigue. Obviously, in terms of ergonomics as well, dry breathing is obviously an important feature. We don't want a regulator in our mouth where every second breath we are taking some water with the regulator. That becomes a little bit uncomfortable for us underwater. So a dry breathing regulator is very important. An easy and accessible purge on a regulator. So if for whatever reason I am needing to clear the regulator of water, that the purge is very easy to access, it's very easy to engage, and it's not a difficult purge to push in order to clear that regulator. We feel that an anti-free flow adjustment is something that is very important. I'm sure you've all heard a second stage knock up against the side of the boat with the cylinder on, and the regulator starts to free flow. This is as a result of Venturi, which we will talk about a bit later. I'll give you the definition that my science teacher gave me when I was at school. But we feel that an anti-free flow adjustment is quite important on regulators because it allows divers to actually down-tune the regulator in certain circumstances where they do not want the performance of the regulator. Good examples of that could be if you're up at the surface and the regulator is out of your mouth and you're chatting to your mates before you go underwater on your dive, you might want to have your regulator on an anti-free flow setting in order to prevent any unwanted free flows. If, for example, you were doing a shore entry into heavy surf, swimming into a strong current, if the skipper says, oh, we've got to do a negative descent on this particular dive because the current is screaming, we may want to desensitize the regulator so that we don't have that performance boost. And then we're down at the bottom, we can then re-engage the Venturi and allow for that performance boost. We also feel that adjustable hose positioning is an important feature with respect to ergonomics as well. Okay, then talking about quality, durability, and reliability. This is quite difficult to be able to answer because when you walk into a store, you don't know what the quality of the materials are used. You don't know the integrity of the design. In fact, I can tell you very honestly that many instructors out there could not explain to you how a first stage magically reduces high tank pressure down to an intermediate pressure. So you can't see those internal things. You don't know the integrity of the design. You can generally, from the outside, see something that is good quality from a workmanship point of view from the outside. But again, this is quite difficult to tell. And then with respect to quality control, obviously that's something that happens in factories, and that's not something that the divers see. So when we look at these QDR characteristics, like the quality, the durability, design, and also reliability, how do you actually judge premium quality when you walk into a store? And to be honest, the best way to do that is to judge it by the brand's long-term reputation for quality and reliability. So who knows whether a Tata is a good, reliable car? We certainly do know that a Toyota Hilux is a very reliable car. So that is, as a result of its long-term reputation, it has been a good quality product over a long period of time, and it has been very, very reliable in the field. Okay. I've just included this as well. It's something that we offer as a lifetime warranty on all of our regulators. So to the original owner of a regulator, that we feel is also a very good feature, but that is not always the case. So let's just have a look at a couple of common features. The first one that I want to speak to relates very much to the second stage. Andrea, can I ask you maybe just to put back onto my camera? I'd like to just show the guys the inside of a regulator and what actually happens on a regulator. I hope this is very clear for you guys to be able to see. But here you can see is a second stage. I'm going to take the faceplate off. Sorry, there is a little bit of a delay in the video here, so bear with me. Sitting underneath there. There we go. Sorry, let me just hold that up. Can everyone see that? Andrea, can you see that? Okay, so yes. Here, right in the center, sorry, there's quite a big delay here, is the inhalation diaphragm. Okay. Sitting underneath this inhalation diaphragm sits a lever. Can everyone see that lever? That's so. Okay, so there you can see, I will try to bring this a little bit closer in. As we are breathing through on the inhalation diaphragm, the lever is sitting on the inhalation diaphragm, and that lever then is depressed as we breathe in. Okay. Now, what that relates to is basically a valve. And to be honest, guys, with respect to whether it's a first stage, a second stage, whether it is a tank, whether it is a BCD dump valve, all valves tend to operate with the same characteristics. So you will generally, on all valves, have a knife edge, which generally when the valve is closed will sit against a seat. Now on the second stage, when I'm breathing on that inhalation diaphragm, it pulls the lever down. What that ends up doing is actually pulling the seat away from the mouth edge. And that allows the airflow to come through to the mouthpiece and for the diver to be able to breathe. Okay, so generally what you will find with all valves is you will have a knife edge, you will have a seat, and you will usually have a spring in 99.9% of the cases. So what actually happens here? When I am breathing, let's have a quick look. I'll try and line this up so that you can see this quite clearly. Okay, so as I am breathing in, I hope you can see this clearly. I'll try and hold it as close to the camera as possible. There we go. Andrea, is that good? Okay, look at what happens when I breathe in through the regulator. Whoops, daisy. So let's just get that to seal. There we go. Okay, have a look at that inhalation diaphragm. Okay, so you can see how that sucks in as I breathe in, and when I breathe out, the diaphragm returns out again. So basically what that is doing is it is allowing the fast flowing air to come through from the regulator. As I'm breathing on the inhalation diaphragm, that brings the inhalation diaphragm down, which brings the lever down. This takes the seat away from the knife edge, and this allows the airflow through to the mouthpiece and the diver's mouth and into my lungs. Okay, so with knowing that information, let us explain some of the engineering that is out there. The first thing to chat about, we can go back to the slide, Andrea. Okay, is Venturi. So the way that my science teacher explained Venturi to me is he said, well, if you are on a highway traveling at 120 kilometers an hour and you're having a cigarette in your car, hopefully you're alone, you crack the window open slightly, and what happens to the cigarette smoke? Well, the cigarette smoke disappears out of the window. Why does that happen? It happens because the fast-moving air traveling at 120 kilometers an hour outside the car, through contact with the static air sitting in the cavity of the motor vehicle, starts to pull that air out of the cavity of the car. What that does is it creates a vacuum where all of those atoms have been removed right next to the window, and that means that the rest of the atoms in the cavity of the car move toward that vacuum to fill the vacuum, which is why it creates a flow of cigarette smoke outside the car. And in reality, on modern second stage regulators, they all have a Venturi effect. Why? Because, as I've shown you, we've got the inhalation diaphragm that is sealing the cavity of static gas inside the second stage, but we have fast-moving airflow that has gone from an interstage pressure of around 10 bar down to ambient pressure as I open that valve, and that is going directly to the diver. As that fast-moving air moves through to the mouthpiece, it starts again through contact to suck that airflow or create a vacuum towards the mouthpiece. And what that does is creates a flow to the mouthpiece. As it creates a flow to the mouthpiece, the diaphragm depresses even further, which opens the valve even further, which creates even more Venturi. You often see guys, and particularly skippers, smacking the second stage against the side of the boat to stop it from free-flowing. All you need to do is close the window. So, in other words, if you just put your finger over the mouthpiece, it would deflect the airflow back into the second stage, and you would stop that Venturi. Why do we have a Venturi assist? Well, the Venturi assist is a power-assisted breathing. So in other words, it doesn't breathe for us, but as we start to breathe, it actually makes the job a little bit easier for us. The other side of that is it also gives me a smooth, easy breathe, irrespective of what depth I am at. Scubapro have always been a very, very big fan of having a diver adjustment to limit that Venturi, as I said earlier. But we do feel that that is a very, very important feature to be able to control. Another important thing to talk about is a variable length demand lever. So this is actually something that Scubapro did very, very early on, the first manufacturer to do that. There are a number of manufacturers that have copied that as the patent has run out, but the demand lever works on leverage. And if you understand leverage well, and you're trying to lift a very heavy object, the longer the stick you use to try and lift that heavy object, let's say I'm trying to lever a rock, if I have a very long stick and I jam it underneath the rock, the longer the stick is, the easier it is going to be for me to be able to lever that rock. Okay, but for quite a big movement on the stick, I will have quite a small movement in terms of the rock. Okay, if I make that lever shorter on the same rock, it's going to be a lot harder for me to lever that rock with a shorter lever, but for relatively small movements on the lever, they will translate to quite big movements in terms of levering the rock. Okay, and the point here is that we like the idea of a variable length lever, which is why we've applied that to all of our regulators, because what it means is at the very beginning of the breath, when you are at that point where you are just about to get the first atom of gas, you're not actually needing a lot of air. What you are actually wanting is easy pull-off. So using the car analogy again, the way to understand this is that on a long lever, the long lever is like first gear in a car. Okay, it makes the pull-off in a car very easy. And to be honest, it's exactly the same on a regulator. With a long lever starting off, it means that your cracking resistance is, or your cracking effort is very, very low the longer the lever is. But if we kept that lever long the whole way through, so in other words, if we only had a long lever, unfortunately that regulator would never get out of first gear. So you never get to a speed of 120 kilometers an hour in first gear. Hopefully you wouldn't, maybe Jose would. But you would have pistons popping through the bonnet, so that's not a very good thing. So what we do is we have designed the variable length lever so that as you are starting to breathe, sorry, Andrea, can I ask you to go back to my video feed again? Andrea? Andrea? Sorry, man. Can I ask you just to go back to my video feed again? Thank you. Okay, so looking at the regulator here, if you can imagine, I'm going to try and get very, very close here. If you can imagine my finger as being, sorry, let me get that into the right point. There we go. No. It's come this way. Sorry, this delay is killing me. There we go. There we go. Okay, so if you look at that lever, I think that's probably the best angle. Look at my finger, which is the point of contact of the diaphragm. That lever is very, very long, but if you can imagine now that my finger is the center point of the diaphragm, as I start to breathe in, look at what happens to the point of contact. My finger starts to run down as the point of contact, and can you see right at the bottom there that the lever for the point of contact has actually got shorter. So guys, this is the equivalent of first gear through to eighth gear in a high performance gearbox. Okay, we're starting off with point of contact as a long lever, and as I'm breathing more and more and more, the lever is getting shorter and shorter at the point of contact on the diaphragm, which is what the diver is actually feeling when they are breathing in or inhaling. Okay. So what we are looking for, sorry, Andrea, we can go back to the PowerPoint slide. So what am I looking for? I'm looking for a car that pulls off very easily or a regulator that breathes very easily, but I also want to make sure that that regulator has the ability to get up to eighth gear and give me the high airflow. Remember, guys, that with respect to that lever, the more movement you have on the lever, the bigger the movement of that seat away from the knife edge. We refer to this in valves, and this is not specific to the diving industry. This is specific to any industry that uses valves. But the distance that the seat moves away from the knife edge, or the knife edge moves away from the seat, we refer to as the throw of a valve. And as a general rule of thumb, the bigger the throw, the bigger the flow. So if I have lots of movement on that lever, it means that I have the low pressure seat moving quite far away from the knife edge, and the bigger I can get those two to move away from each other, or the bigger the throw, the bigger the flow I will get through the regulator. So what you're getting is smooth, progressive air delivery that is easy to control. It's easy to breathe, it's easy to crack the regulator, but when I am needing high flow from the regulator must be able to do that for me. So we feel that a variable length lever is a very, very important feature. You'll be surprised at how many regulators are out there that do not have variable length levers. So the guys have a single length lever that maybe they choose third gear. It's not very good from a pull-off point of view, and it's not exceptional from a flow point of view, but it is a good, easy medium in the middle. Okay, we were talking about regulators in terms of metal second stages. The one thing that we do try and reinforce is the difference between a plastic or lucky packet second stage as opposed to a polymer or a reinforced nylon casing as most manufacturers are using. Scubapro definitely use that. We use an amorphous polyamide nylon, which is reinforced. It is exceptionally durable, and it also allows us the ability to polish the inside of the regulator to a very, very smooth sheen so that the drag coefficient is reduced. We have minimum resistance of the airflow traveling through the regulator into the diver's mouth and down to their lungs. So fiberglass reinforced case is a better option than a typical plastic regulator. So what does that do? It adds strength, stability, and rigidity. I can tell you very honestly, on this regulator here that you see in the picture, this is an S600. We tendered to the Department of Defense in the early 2000s, and they were very, very concerned of moving away from a metal second stage onto what they saw as a plastic second stage. Luckily for me, the chief warrant officer is a 160 kilogram guy. And I put an S600 on the concrete floor for him. And I said, what I want you to do is stand on the regulator. And once you've got your balance on the second stage on the concrete floor, I want you to jump as high as you can and land on the regulator. And if you can break the regulator, I will give you and your wife one for free. And obviously, he didn't manage to break it. So, guys, it is quite important. If you had to do that on a plastic second stage, yes, you would definitely have some damage. The amorphous polyamide or the fiberglass reinforced case that we use means that the regulator is virtually indestructible. And in actual fact, we, by accident, reversed a Land Cruiser over an amorphous second stage. The only thing that broke was the mouthpiece. And I can tell you very, very honestly, if you take a 2-ton Land Cruiser and reverse it over a metal second stage, you are more than likely going to have some change in the atomic structure of that regulator. So this is the move that we have made, is to the nylon reinforced case. The other thing that I would like to talk about here are hoses. So generally what you tend to find is that the conventional hoses that are out there have a small internal diameter. They have a small outer diameter. And what that means is, and guys, again, this is very, very much the same on all valves that are out in any industry. It's not specific to the diving industry. But generally, if you have a constant supply pressure, so like we were talking in the second stage hose or the interstage pressure of 9.5 bar moving through your regulator hose toward the second stage, you basically want that to be moving as easily as possible. But now, for a constant supply pressure, the bigger the bore or the internal diameter of the hose, the bigger the flow as well. Okay, so in terms of conventional hoses, what you tend to find there is ergonomically, they are very flexible and comfortable. The diver moves their head in any direction, up or down, left or right, and they don't feel like they are fighting their regulator. It's very easy for them to move around. The disadvantage, obviously, of a conventional hose is that you have poor airflow. On the opposite end of the spectrum, you have a wide bore hose. So as we've said, for a constant supply pressure, if the bore is bigger, then your flow will be greater. Okay, so the obvious benefit of a wide bore hose means that you have very, very good airflow. But as I said a little bit earlier, you've got to be careful there, is that those hoses, because they are very, very big, are very stiff. They're very uncomfortable. So the diver tries to turn their head to the left and the regulator pulls their head back in front again. Okay, also the weight of the hose is felt from the mouthpiece because the diver is holding not only the weight of the second stage, but the weight of the hose as well. So they're stiff and a little bit uncomfortable. Okay, what Scubapro do is we've got the best of both worlds there. What we do with our hoses is we Kevlar reinforce the hose. And what that means is that the internal diameter is very big. It's got a small outer diameter, which means that the walls are very thin. But what we do to reinforce the reliability of the hose is we reinforce it with Kevlar. And in fact, that particular hose has a 250 kilogram braking strain. And in fact, for that same warrant officer, when we won that tender as a preferred supplier to the Department of Defense, we claim that we've got a 250 kilogram braking strain. They said to us, well, you have to supply a certificate for it. So I had to take the hose off to the CSIR. We did a high tensile strength test on the hose, and the hose broke at 262.3 kilograms. Okay, so that's not to say that you're going to be pulling your divers out of the water by the hose because it's got a 250 kilogram braking strain. But what it means is that you have the best reliability, durability of that hose because of the Kevlar reinforce. The hose will also not collapse and cut off your air, much like you do with a garden hose, and you'd be surprised at how often that can happen on diving regulators as well. You can dramatically reduce the performance if the hose collapses. So you should be looking for a hose that is a non-kink, non-collapsible hose. And also my recommendation with respect to hoses, we see these new colorful hoses that are out on the market. I'm sure you guys have all seen them. Guys, you've just got to be very, very careful. Yeah?
Sorry for interrupting you. Also talking about hoses, we got two questions that I think that covers also your things that you were going to say about the colorful hoses and things. Would you like to hear them.
Talk about those. Okay.
Yeah,
Yes.
the first one is from Gregor Smith that asks, talking about hoses, what are the differences between Miflex and normal hoses?
Okay. I'll tell you very honestly with respect to that. And guys, sorry, man, I obviously work for a manufacturer, so I don't want to come across as unprofessional. But I can tell you very honestly, in terms of those hoses, the best recommendation that I can make to you is that if you have a Mares regulator, use a Mares hose. If you have an Aqualung regulator, use an Aqualung hose. If you have a Scubapro regulator, use a Scubapro hose. And the reason why I say that is what I'm actually going to refer to what I said earlier is remember that the interstage pressure is the supply pressure to the second stage. Now, remember that I said different manufacturers have got different interstage pressures. So you'll have one model of regulator that operates on an 8-bar interstage pressure. You might have a different model of regulator that operates on a 13-bar interstage pressure. The point here is that you cannot choose a generic internal diameter and hope for the best. You have to know what the interstage pressure of that particular regulator is. So in relation to that, if a manufacturer, and some manufacturers do, they will go to someone like a MyFlex and they will say, guys, I want you to design a hose for me. It needs to be 75 centimeters in length. I would like it to have an outside diameter of this, an internal diameter of that, and I want it to be made out of the following material. Well, then you can have all of the colorful things from the fashion point of view. If it is made to the specification of that particular regulator, then it is correct. Scubapro, I can tell you in Europe, if you take a Scubapro regulator with a generic hose on the regulator in for service, Scubapro will actually return that regulator after servicing with the hose separated from the first and second stage. We feel that it is unsafe to choose a generic internal diameter for all interstage pressures. You cannot do that. There have also been some questions around kinking of those particular hoses. And to be honest, there's no real major difference to that question, Greg, if you have to take a normal, for example, a Scubapro hose, and you take the black rubber coating off the hose, guess what you find inside? Precisely what you see on a MyFlex hose, except on the Scubapro one, it has Kevlar reinforcing. So in my mind, I don't see why you would want to then remove the coating of the rubber. And as I say, unless the manufacturer has gone off and asked for the specific specification of that hose relative to their specific first stage, this is not something that we would recommend.
Okay.
Does that answer your question, Greg?
I think that would answer his question. Then let's see if he answers. Then the second one is from Sandra Zwart, and she says, what are the best hoses to use in the tropics, and what do you think about the braided hoses? Sorry, I think it's pretty similar.
I think I've answered that. And again, we've got to understand there, Sandra, that with respect to the hoses, again, you would want the most protection on the hose possible. So whether you're in the tropics, and to be honest, whether you're in the tropics or you're doing ice diving, you want the highest quality hose that you have available, because this is linking your life support first stage to your life support second stage. Make sure that it is a high quality hose. But maybe just to end that off, Andrea, if everyone is happy, again, I'd like to just reinforce, use the manufacturer's specification with respect to the first stage that you're diving.
Okay, perfect.
That's okay?
I think you were pretty clear. I'm going to go back on your presentation.
Great. Thanks, man. Good questions, guys. Keep them coming. Okay, so I think we've covered the hoses there as we've moved through. One thing I'd also like to talk about is just the exhaust valve. Remember that one of the features that we were looking for was easy clearing of the regulator. I want to easily be able to clear my unmetabolized oxygen as well, or gas, as well as the carbon dioxide that I'm breathing out of the second stage. So the one thing that has happened between the 80s, 90s, and into the 2000s, obviously we have more children diving. We have more female divers than we ever have had before, which is great. And the reality is, because of those things, you will find that second stages generally have got a lot smaller. Okay. Now, the problem with that is as the regulator has got smaller, a number of manufacturers have made the exhalation bore smaller as well. Now, remember what we were talking about with respect to the hoses? And guys, this is an important thing, is you can't turn the physics off. If you have made the exhalation bore on your regulator smaller, or it's using a standard size exhalation, remember that for a constant supply pressure, the bigger the bore, the bigger the flow. So the smaller the bore, the smaller the flow. So if I've got a very small or standard exhalation exhaust, it means that I'm expending more energy breathing my unmetabolized O2 and carbon dioxide out of that regulator. So what you should be looking for there is a large bore exhaust valve. So you can see the picture there. But the bigger the bore, the harder it is to actually seal that exhalation diaphragm. And guys, it's like a butterfly valve, the same kind of valve that you would see on the end of a vented snorkel. Very similar, made out of 100% silicon in most cases. And as I say, with respect to that, it allows you to exhale your unmetabolized gas and carbon dioxide out of the regulator, but it doesn't or shouldn't allow any water to leak into the second stage. What Scubapro do with ours, and a number of manufacturers are starting to do that too, is the sealing lip on the edge of the big bore exhaust. And because you have hydrostatic pressure or water pressure pushing on the outside of the diaphragm, it flattens that little lip and that creates a seal. So it makes it quite easy to lift when you are exhaling, but when you've stopped exhaling, that little butterfly valve seals back again. Okay, so very, very important from that point of view. Guys, one other important point there, and I don't want to get too technical here, but actually what is quite funny with respect to an exhalation valve too is that if we look at that diameter of the Scubapro valve, I can tell you our exhaust valve, it's 29 millimeters in diameter, so let's call it 3 centimeters. And if we say from diving physics that for every 10 meters of seawater, there is a change of 1 bar or 1 atmosphere of pressure per 10 meters of seawater, that means that for every centimeter of depth, we have 1 extra millibar of hydrostatic pressure. Okay. Now, if you had a GoPro camera that was a miniature GoPro camera that you could put inside a regulator, I can tell you as well that what you will see from most of those is only the top of the exhaust valve opens. Andrea, sorry, man, can I ask you to go back to my screen? I just want to show you something. Thank you very much. So there we are talking about the exhalation diaphragm. You can see that. I don't know if you can see here on this exhalation cover, there is a vertical bar. That vertical bar basically sits on the center of the diaphragm like that, and it means that it forces the exhalation valve to open. Sorry, I'm just trying to get the clearest angle. Open like a book. Okay, so what that means is that I get the whole bore or diameter to open because of that bar. You'll be amazed at how many regulators don't have that. So as I say, if I've got 3 millibars extra pressure on the bottom of the diaphragm and 3 millibars less pressure on the top of the diaphragm, what that will do, remember the airflow, like water, will take the path of least resistance. And what that means is, if you had a miniature camera on the inside, only the top of that valve opens, which means that I'm actually getting half of the bore of the orifice to get the flow out of the second stage. Okay, which is why we put that little separator bar there on a Scubapro regulator. This cannot happen. That bar prevents the valve from opening top only, and it ensures that the valve opens left to right like a book. So in other words, I'm getting the whole bore, big bore, to open. The bigger the bore for constant supply pressure, the easier my flow, which means that it is much easier for me to clear my unmetabolized O2 and carbon dioxide out of that regulator. Thanks, Andrea. We can go back to the slide. I see we're at about 20, what are we? We're about 50 minutes in, hey? So I'm gonna go quite quickly, guys. So just one very, very quick thing that I'd like to talk about, and then I think what we should do, Andrea, is open it up to any questions that any of the divers have, is I'd like to just talk about the Ansi machine and the EN250A 2014 standard. It sounds like a mouthful, but it actually is quite a simple thing. In that picture up at the top there, you can see one of our lead engineers, Corrado. In fact, the C370 second stage, the C stands for Corrado. And Corrado is standing in front of our Ansi machine that we have in Italy. We have another one in France as well, and we have one in Germany too, as well as in the States, but talking from the European supply. And what the Ansi machine is a machine that is used for the European norm standards. So I'm sure all of you have seen the CE stamp on various products, whether it's an air conditioner or a baby chair or a seat belt. In order for manufacturers to supply their products in the European Union, they must pass the European norm for that particular product. Now, the European norm for diving regulators in the European Union is the European norm 250A 2014 standard. It's changed slightly in 2014. And basically what they do with respect to this machine is it is an Ansi or a UK designed machine. And what the machine allows us to do is basically connect the regulator to the machine, and we can change a whole number of parameters. So in the case of the machine, you see Corrado standing in front of there. It is actually a hydrostatic machine. So in actual fact, you immerse the regulator in water. The regulator is connected to an artificial lung, and the machine basically breaks down how many joules you expend breathing 1 liter of gas. Now, what is fantastic about this machine is that it cannot read a brand name. Okay, so in other words, guys, this is the same as we do in motor vehicles. When we say a car goes from 0 to 100 in X amount of seconds and its fuel efficiency is X. We test all cars relative to that, and this gives consumers some key information to be able to make an informed choice. To be honest, that is exactly what the European norm and the Ansi machine do for us. So I'd like to just show you, without getting too complicated about it, what the little Ansi graph looks like. Okay, so there you can see. Can you see my pointer on the screen there, Andrea? No. Okay, let me just try something quickly. Okay, it's not going to allow me to do that. Okay, but you can see with respect to the graph there that there is a 1, a 2, and a 3. So this is what a work of breathing graph looks like. Now, for the EN250 standard, what they do is and it's quite an aggressive test to be honest, is they take all regulators that manufacturers are wanting to sell in Europe on the Ansi machine down to a depth of 50 meters. They supply 50 bar of tank pressure. So as if you were at 50 meters with 50 bar in your cylinder. I hope you're never in that situation. So worst tank pressure, deepest possible depth, talking from a recreational standpoint. And what they do is they activate the lung to draw 25 breaths per minute at a volume of 2.5 liters per breath. Okay, it is what is referred to as an RMV, or respiratory minute volume. And the respiratory minute volume basically is giving you what you are breathing in liters per minute. Okay, so for those of you that are very good at maths, 25 breaths per minute times 2.5 liters gives you an RMV of 62.5 liters per minute. Now, what I can tell you is 62.5 liters per minute is a relatively stressed diver. It's a donkey on the edge, someone who is considering bolting for the surface. So in other words, it's putting the regulator through the worst case scenario. Now, with respect to the graph, you can see the graph starts where the figure 1 is. You can see that the axis that is horizontal is liters of flow, and the vertical axis is millibars of pressure. Okay, so when you begin your inhalation, so just as you're starting to breathe from the regulator, that is where 1 starts. The Millibar moves down the line. So if you look at the liter line that is horizontal, the line comes down to the bottom of the page, and you can see that you have millibar reading there, but with no horizontal movement for liters. This is referred to as the cracking effort. In other words, the amount of energy you expend just before you get that first atom of gas. As the line starts to move towards the 2, you can see that I'm starting to get some liter flow there. And that whole section of 2 sitting underneath the horizontal liter line is your inhalation. And this is referred to as the inhalation effort. In other words, the amount of energy that you expend keeping the valve open during normal inhalation. And then segment 3, to close the loop of the work of breathing graph, you can see is the exhalation effort. So at the beginning, there is a little bit of tension or millibar movement before I've got any liter flow out of the exhalation diaphragm. And then you can see that the loop starts to close back to 1. And guys, what we are aiming for here is the smallest possible surface area of that graph. The lower or the smaller the surface area, the smaller the work of breathing of that particular regulator. Okay, so work of breathing is made up of cracking effort, inhalation effort, and exhalation effort. Let's show you a graph that is a more realistic graph. Sorry, give me a second. So for example, here is an actual Ansi graph. This one happens to be on a Mark 25 S620 Ti. And with respect to the graph, you can see the movement there and how small that graph is. Where you see the inhalation going above the liter line, guess what that is? Venturi. That is your Venturi assist, where it is a positive pressure above the liter line. You cannot have too much Venturi or your regulator will fail the European norm and you may not then sell it in the European Union. So there are some parameters in terms of not having too much power assist. But generally for regulators to be sold in Europe at 50 meters, 50 bar, 25 breaths per minute at 2.5 liters per breath, a regulator must perform at under 2.5 joules per liter. To be honest, there are probably about less than 30 regulators in the world of all brands that are below 1 joule per liter under those particular parameters. What I can tell you very honestly with respect to our Scubapro range, including our entry-level rental regulator, the Mark II Evo with R095 second stage, all of our regulators are below 1 joule per liter. Now, that is quite interesting when we talk about balanced versus unbalanced. I hear many instructors saying, whatever you do, buy a balanced regulator. And I've got to say very, very honestly to you, I would much rather, if my budget didn't allow for it, I would much rather buy a well-designed, unbalanced regulator than a badly designed, balanced regulator. You can find cheap regulators in China made out of plastic that are balanced in design, and I can tell you very honestly, when we put them onto the Ansi machine, they fell at between 15 and 20 meters. They can't reach the parameters that are required for the European norm. And in some cases, actually, guys put a fake CE stamp on the regulator as well, which is quite funny. Guys, I'd like to just end that off there because I think we've been quite long. I said to Andrea, we wanted to make sure that this was kept very, very short. I think what we can do now, Andrea, is maybe open it up to questions if there are any questions. And guys, what I'd encourage you to do as well, this is something that we would like to do in the long term. So if this is something that is valuable for you guys, please, you're more than welcome over the next week or two to post your questions to either Andrea or myself, and we'll do our very best to be able to answer those questions for you at the next session.
Yeah, okay.
Andrea, over to you.
We have some questions, but before I
do?
would like to say sorry to all our Facebook friends because we had a problem and actually the live stream on Facebook is not working, so I just posted the link, and for next time we will make sure that it's gonna work.
Great.
And going back on questions, we have the first question from Gregory Smith, because the one that I asked you before was his second one. The first one is actually asking, What regulator do you suggest to buy? A DIN or
Good
an
question.
INT one? So I think he's saying, yeah, a DIN instead of a clamp or yoke, how
Yeah.
they say in the US.
Yeah.
And what are the main differences between the two? And thank you so much.
Great stuff. Greg, it's a fantastic question. So basically what Greg is asking there, and I think most of you are aware of it, is there are two different formats of first stage. You have international, sometimes referred to A-clamp or yoke, and then you have DIN fitting. Now, I would say that probably in the 80s, 90s, you would find that all technical divers were generally diving DIN fitting. You wouldn't see a technical diver diving an A-clamp fitting. The reason why A-clamp regulators were designed, to be honest, has actually got more to do with tank valve manufacturers. Now, we had some tank valve manufacturers that manufactured their tank valves without a removable insert. So in other words, the tank valve could only accept an A-clamp regulator. What I will say is that this has become less and less common. To be very honest with you, when I'm cave diving, I can tell you I will never use an A-clamp regulator. And the reason for this is on a DIN regulator, the sealing O-ring actually gets screwed into the back of the valve. Whereas on an A-clamp regulator, you note that O-ring is actually sitting right on the surface of the tank valve. I'm sure you guys have all heard a tank valve O-ring blow. It's quite an exciting process. It's a big bang, sounds like a gunshot. And that is generally something that will only happen on A-clamp regulators because that O-ring sits very, very close to the surface. You've got to bear in mind that you've got 200 bar of pressure trying to extrude that O-ring. So if the O-ring is slightly worn, or if the fitting between the A-clamp and the tank valve is not that good, you can have an extruded O-ring. But to be honest, on a DIN fitting, this is almost impossible to happen because that O-ring sits right at the back of the valve. So if you are asking my advice, DIN versus INT, I would say DIN every day of the week, including Sundays. I would also say that with respect to that, there is no pricing difference generally between manufacturers of INT versus DIN. As an indication, I would say that probably in the 90s, we were probably selling, I would say 70% A-clamp versus 30% DIN. I can tell you very honestly today, we sell 95% DIN, 5% A-clamp. I think now as recreational divers start to understand the benefits from the technical diver point of view, all of the benefits to technical divers are the same benefits to recreational divers. So there's no difference from that perspective. So yeah, to answer the question in short, Greg, DIN definitely above A-clamp.
Yeah, if I may add a couple of things, I think that pretty much in Thailand and US is more used the A-clamp valve, the A-clamp system than the DIN.
And sometimes in Australia as well.
Oh, I didn't know
Australia
that.
quite common there as well, yeah.
And I had an experience where a client came and said, "Can you have a look at my regulator?" And he had a A-clamp regulator that actually had bubbles in the A-clamp, in the molding of the A-clamp, and actually cracked, and it was pretty much open. And he said, "Is it normal? Can we change it?" As it is better maybe if you buy a new one. And
a new one,
yeah,
exactly.
It's better if you go straight with DIN. That for me it's much safer.
Yeah,
then,
absolutely.
Going on another question, we have a question from Jacques Vieira, and he is asking, because I think he knows you, that you are South African and you live in South Africa and working for Scubapro South Africa. He is asking, has South Africa made any dive equipment like regulators? Thanks.
Okay, on the regulator side, Jacques, thanks. Hi, and how's it to Sandra and Joe? I'd like to say that with the regulator side, we are not manufacturing anything in South Africa from the regulator point of view. My partner, Reese, who runs Ender Summer Technologies, is a vendor to Scubapro and also a designer. So Jacques is very aware of this. I think this is maybe for the benefit of everyone, is we have designed, Reese is the designer of the Seawing Nova fin So that is proudly made in South Africa and applied to Scubapro. And I think our latest stats are this has been the top-selling fin in Scubapro's history, even in comparison to the jet fin from a quantity perspective. So we make the fins. Jacques, you will also see, I think it's a cut here as well. You will see the Go rental fins. This is also a South African design, but sold to Scubapro. So we make it here in South Africa for Scubapro, and we export it around the world to Scubapros there. And then we have also made the Hydros Pro BCD, and maybe that's a nice topic for next time. We can talk about BCDs. Depending on what information you guys want to chat about. But the Hydros Pro is a very revolutionary BCD. It won the best new product at DEMA just before COVID, pre-COVID. And this is something that we make here in South Africa. Jacques has exciting information, and I'm actually just questioning whether I should be telling you this information. But we are also going to be designing the full technical range. We've designed the full technical range, and that is also going to be made in South Africa. So the new S-Tech line, so that's down to stage kits, backplates, harnesses, wings with accessory pockets and expedition reels and all of that good stuff. We have been beta testing and prototyping for the last couple of years, and we are hoping for a global launch in June. I think Europe are deciding 1st of June as the, 1st of July as the launch. So that is a new exciting product that we've been spending many hours underwater with and refining. Yeah, good question. Thanks, Shad.
Great. So moving on technical, I have a couple of questions also that include a bit of technical diving. That is, the first one is from Consulenza 360, I think it's Italian, and is asking
ciao.
And is asking, what is the difference between split fins and fins like the jet fins, so the technical ones?
Okay, great. Well, we are very good people to speak to about this as Scubapro, because we were one of the very early adopters of split fins. Andrea, can you give me 2 minutes? I'm going to run downstairs quickly, and I'll be able to explain this very, very easily.
Okay,
just give me
want,
not even a minute. It's going to be a second. Okay, will you grab a split fin for me?
Yeah,
that'd be great. I'm going to grab a Seaving Nova.
Okay. So, meanwhile, split fins are called split fins.
Yeah,
because,
yeah, in fact,
great.
There we go, a twin jet fin. Thanks, Andrea. Let me just put my earpiece back in. Okay, great. So that's a really good question, Consulenza. So I'd actually like to go back before the split fins and just give a little bit of information, if you guys are interested to hear, just to talk about what the function of a fin is. So the function of a fin is actually, it's quite difficult, to be honest, because we're trying to move this thing up and down to create movement horizontally. So there's vertical movement on the fin, but we're trying to get horizontal movement. Okay, so typically in terms of fin design, what we tended to find is that, and maybe to simplify this, what you're trying to achieve with a fin is basically a 45-degree angle of attack. If I can get the water as this blade is coming down to hit the blade at 45 degrees, it will deflect back at 90 degrees, and that is my best shot at propulsion. Make sense? Okay, but what happens on most fins? Most fins bend like this, which means that you actually only have a very, very small band of the fin that is at the 45-degree angle of attack. So the point here is that it's quite a difficult job with respect to fins in terms of old fin design. What most divers used to do, and certainly that's what I did when I started diving in 1991, is you look at what your instructor is wearing. But now what you forget is that your instructor has got very, very well-developed swimming leg muscles because he's been diving for years and has got thousands of dives under his belt. So are those fins the right fins for you as a beginner diver? And this was the problem we always had as manufacturers with respect to fins, is it was quite difficult to match the correct fin to the correct diver. So, to be honest, the best thing to put on the end of your leg would be a plank of wood. But you would need leg muscles like Arnold Schwarzenegger to be able to move that plank of wood through the water. Okay. On the opposite end of the spectrum, you've also then got the efficiency of the fin. So basically, we are fighting two things, speed versus efficiency. Traditionally, we used to have very, very good performing fins, industry standards, things like Amaris Quattro, Cressy Master Frog, number of fins that were out there as normal paddle fins that were very high performing fins, but unfortunately not very efficient fins. Enter the split fin. So I'll tell you the story behind the split fin. The split fin is run by a guy who runs a company called Nature's Wing. Scubapro were a very, very early adopter of the split fin technology. I think he was much smarter than us because he patented the split, and then every single manufacturer for every fin they sold gave a royalty over to Nature's Wing. So you'll see every split fin that's out there, whether it's a Tusa, Apollo, a Scubapro, a Mares, it doesn't matter. All of those fins will have the little Nature's Wing badge on it, and I'm sure he's sitting on his own island sipping pina coladas on a hammock now. He made a lot of money as a result of that, I'm sure. So the split fins, the idea of the split fin, and if you can hold that up for me, Andrea, the idea of the split fin is that that fin doesn't bend. It actually splits open. Yeah, exactly like that. Exactly as Andrea is holding it now, that is what the fin does underwater. Now, if you look at those, basically, he has chosen, this particular guy had very little to do with diving equipment. He was actually an aeronautical engineer. And I don't know if you guys have heard of Bernoulli's principle. You probably have. It's what has created flight on the planet today. And Bernoulli's principle basically says that on an aircraft wing, if I make the one side of the wing a slightly longer distance and the bottom side of the wing a shorter distance, as I am running the aeroplane down a runway, the air that travels the further distance creates a low pressure, and the air traveling the shorter distance underneath the wing creates a high pressure. And like a weather system, the high pressure tries to move toward the low pressure. And to be honest, that's what it does with the split fin, is the split fin actually works on Bernoulli's principle. And what he was saying is that if the principle, Bernoulli's principle, holds true for aircraft design and aeronautical engineering, well, then it must hold true for hydrodynamics, and in fact, even more so in hydrodynamics, because we have more particles closer together in the liquid of water. So he was a very, very clever guy. He didn't design a single mold. So in our case, Scubapro paid for and built the molds and then paid over a royalty. I think the second guys that were adopters were Apollo. And then I think Tusa, there were 7, 8, 9 manufacturers, I think, at that particular time. So the big benefit of the split fin was that irrespective of the customer that you had standing in front of you, whether this guy had 5,000 dives under his belt or was doing their first sea dives tomorrow morning, you could recommend a split fin. And the split fin actually was exceptional from both a speed point of view and from an efficiency point of view. I'm talking generally with respect to the split fins. There were some split fins that were designed by manufacturers that weren't very good. But I can tell you very honestly, on something like a twin-speed full-foot split fin, this still remains one of the fastest fins in the world, okay, from a split fin point of view. But we weren't really looking at it from the speed perspective. They were really looking to get speed and efficiency matched, which wasn't the case in the industry there. What I will say to you there is that the disadvantage of split fins is A, acceleration. Okay, exactly the same as you need a runway for Bernoulli's principle to work on an aircraft wing. It takes quite a long time in terms of your kick cycles to get to a point where that Bernoulli's principle starts to work for you. So instantaneous acceleration was not very good compared to a high performance paddle fin. Okay. Second problem that we had with respect to split fins, and I can tell you very honestly, this was the same for me. I dived the first prototype on the produce at Aliwal Shoal. It's a wreck in South Africa, just outside of Umkomaas. It's about a 30-meter dive on the sands. And I took the first prototype of the one that Andrea's holding in his hand. It was a gray one, but it was the first edition twin jet. And I was used to diving at that particular point a Veloci Gorilla, which was a P-Bax Gorilla. It had metal flex in the blade, and I could actually stay up to the same speed as an underwater scooter, our sea glider, which did about 2.2 k's an hour. But I can tell you, after 50 or 60 meters of swimming next to the sea glider, completely exhausted. Okay, so from an efficiency point of view, not very good. I put these fins on, and I can tell you my first response was, I hate these fins. I don't know how we're going to sell them. Because what you don't realize is that most instructors up until that point were using the stiffness of the blade to determine the performance of the fin. What was quite clever is that this guy from Nature's Wing designed an underwater speedometer. So all of these instructors that were used to diving very stiff blades, when they moved onto the split fins, felt like they were diving in a pair of booties because there was no resistance on the blade. The blade was opening up and allowing the water through. It felt terrible. But the guys were amazed at the speed they could get from the fin. The third problem with respect to split fins is that when divers are turning to swim hard, so let's say, for example, I have to swim into a current for whatever reason, I turn, and what do I do with respect to my kick stroke? I increase the amplitude of the kick. As I'm increasing the amplitude of the kick, I'm also increasing my drag because of the amplitude of that. The best way to explain this to you, and in actual fact, a boat propeller works on Bernoulli's principle as well. You've got a long end and a short end of the propeller, and if you're trying to increase speed on a boat, do you increase the diameter of the revolutions? No, you don't. You increase the frequency of the revolutions, but we could not get divers to do a shallow flutter kick in fast cycles. Instead, they did big kicks like this, which increased the drag. So you actually, on a split fin, slowed down. It was a very common thing that we heard from divers. Guys said, oh, love split fins, they're amazing, but you can't swim into a current. And guys, the reality is that if a fin can do 2.3 kilometers an hour, and the current is at 1.8 kilometers an hour, well, then you should be able to swim into the current. But if you increase the amplitude of the kick, then you might slow down. And to be honest, just one last third point to wrap up on the split fins. The third point, and particularly for areas that are diving on ribs or rubber ducks, where the draft of the boat is quite high, at the end of the dive to try and get onto the boat, remember that on a paddle fin, you are actually able to stand on the blade and on the water to get up onto the boat. Obviously, that doesn't work very well for the split fin. So we had a couple of divers that were really, really battling to get out of the water at the end of the dive. So that was a disadvantage of the split fin. To be honest, what we then did was the Seawing Nova. So from a Seawing Nova point of view, sorry, can we go to the main screen there again, Andrea? Sorry.
Yes.
I'm trying to just stay in my small screen. The Seawing Nova, which was the design there, and this, to be honest, has been rated as the highest performing fin, but also with almost the highest efficiency with respect to fins that are out there. What we've done here, you can see it's quite a weird cross-section in terms of the blade. Sorry, I'm going to just try and hold that for you angle-wise. But this fin cannot bend like traditional fins do. And what we've done is we've actually borrowed some technology from aeronautical engineering as well. It's a very fancy term for a very simple thing. In aerodynamics, it's called tetradihedral aerodynamics, in this case, hydrodynamics. But what happens on a Seawing Nova fin is that when you kick, the blade actually scallops like this, which creates a rigid spine, which means that the blade cannot bend like this. The blade actually bends like this. Goes like that first, and then it gets to the 45-degree angle of attack. What is great with respect to this is that it gets to the 45-degree angle of attack, whether you are kicking efficiently or if you're clicking flat out into a current. It won't overextend and it won't underextend. it stays at the 45-degree angle irrespective. One other thing that we've done just in terms of the design philosophy there as well is this area of a fin generally is built up. You've got to bear in mind that in the Keck cycle, if you can imagine a horizontal diver here, this section of the blade is actually deflecting water backwards. So this is actually taking you backwards. Okay, so it is creating drag, which is why we have removed as much of the real estate away to reduce that drag. All right. And to be honest, looking at the jet fin, I still dive jet fins in the cave on every single technical dive that I do in the cave. And the jet fin is just an exceptional fin as a short fin, as well as being a single material fin. So it's not a composite plastic, which is kind of what we've done on Seawing Nova as well. It's made out of a material called monprene, and it is a single material throughout the fin. So it gives you those same types of benefits, but even better. So I would say that probably in answer to that, Seawing Nova is the best combination between a high-performance paddle fin, but with the efficiency of a split fin.
Okay.
Hope that answers the question.
I think you were pretty clear. And just to say, I use split fins since a long time, and I never had a problem, even in current. You just have to do short, flutter kick, or I can even do frog kick with no problems. And I also found my way to fin to actually kick in the water, and really no problem, even in strong currents. Then,
so sorry, one thing, sorry, Andrea, just to close off on that, one thing that I would like to say, I've obviously got a vested interest. I'm in the industry. I have a vested interest to dive Seawing Nova in the cave, to be honest. And it's funny, the one point that I would make there is choose the correct weapon for the war.
Yeah.
Okay, so if you're going free diving, use a free diving fin. If I'm going cave diving, I use a jet fin. If I'm doing an open water sea dive in the sea, I will use my Seawing Nova Gorillas. On a typical recreational dive, I use my closed heel Seawing Novas. You choose the correct fin relative to the environment and what you are trying to achieve on that particular dive. But again, what we're looking at there ultimately is efficiency versus speed. That's what we're after, yeah.
Perfect. I think you were really clear. Then we have another question from Gregory that he's asking, is backplate and wings really the better solution for diving, also for travel?
No, it's not. It's not. You know, we laugh about it. You get onto Scuba Board and places like this, and we actually call it the BPW brigade. You know, backplate and wing. I see entry-level customers getting onto the chat room there saying, guys, what do you suggest I buy? And then you have this BPW brigade that just launches into this poor guy that is just trying to get his first BCE, saying, you must go backplate and wing. And guys, the reality of that is exactly the same as the fins. Choose the correct weapon for the war. So I don't feel that you could take a stainless steel backplate or an aluminium backplate for that matter and say that that is perfect for everyone. So for one thing, female divers, hips are higher, torso length is shorter. It is just physiologically the case, which means that a backplate that is long may be very, very uncomfortable for a female diver. So I wouldn't say that backplate and wing is the better solution for diving. Backplate and wing is definitely a very, very good solution for diving if you're diving twins with side slung cylinders and a whole bunch of extra equipment. But I cannot accept that a backplate and wing is better than something like a Hydros Pro for your typical recreational diving. And I don't buy that. I argue people out of buying backplate and wing from a recreational point of view.
Okay. Now, I'm seeing a lot of posts on the social media where people are just saying, go straight backplate and wings, go backplate and wings.
Okay. So, I mean, choose the correct thing, you know, for the correct environment. And as I say, I can't accept that that is the case. And again, you know, I mean, I wouldn't want to travel with a stainless steel backplate, and then you've got to switch to an aluminium backplate, and you undo your whole configuration to be able to have an aluminium backplate just because you're going traveling. You know, I, again, would rather choose a recreational style BCD. Something for me like a Hydros Pro meets my requirements perfectly from a recreational point of view. And I'm also very, very comfortable to have 1 or 2 stages on something like a Hydros Pro. But if I'm doing a 4.5-hour dive in the cave, well, then I'll definitely use a stainless steel backplate and the correct lift that I need for that configuration of gear. And I guess that's the other point as well with respect to the wing sizes, Greg, is which wing size do you choose? You know, I do a lot of adventure motorcycling, off-road riding, and there's constantly the debate of which is the best on-off-road tire. And the point is, it doesn't exist. Because if you find something that is pretty good off-road and pretty good on-road, you can definitely find an off-road tire that is excellent off-road and terrible on-road. But you can also find an on-road tire that is excellent on-road and terrible off-road. So again, it depends on the environment you're diving. Choose the correct thing for that particular environment would be my best suggestion or recommendation. Yeah.
Okay. Just we have other question from Consulenza and other people, and I would like to read that there is Michael Ribeiro. I hope that I'm pronouncing right.
Hi, Michael.
That says, "Thank you, Steve. You're a born communicator. Lots of valuable info." And then he asks, "Any tips on daily cleaning regulators?"
Excellent. Yeah. Good question. Sorry, I see it's Miguel. Sorry. I didn't mean to call you Michael. Miguel. Yeah, Miguel. Miguel, with respect to cleaning regulators, again, the very daily cleaning of regulators, definitely rinse the regulator in fresh water. I generally recommend that you try and rinse it in fresh water that is quite warm. Obviously, the warmer the water is, the easier it is for the suspended particulate like salt water that is adhered to the regulator to dissolve into the solution and wash off. Obviously, the typical things like don't rinse your regulator without the dust cap securely fastened. Guys, very interestingly on that, sorry, just I know that's a small point, you know, rinsing with a dust cap on or off. We've actually physically seen this on the Ansi machine. If you rinse a regulator with the dust cap off, remember I was saying Mark 25 Evo supplies over 10,000 liters worth of flow, more than 4 stressed elephants can breathe at 100 meters. If you rinse a regulator 4 to 5 times with the dust cap off and you get water onto the conical filter that sits under the dust cap, you can reduce the flow rate of a regulator by up to 50%. And I've physically seen that. So you've got 10,000 liters worth of potential flow, that now drops to 5,000 liters worth of flow. If you're on a regulator that was giving you 2,000 liters worth of flow, you're now on a regulator that gives you 1,000 liters worth of flow. So make sure the dust cap is on. The usual sort of stuff as well, keep it out of direct sunlight as much as you can, store in a dry, cool place. And I would also say that with respect to that, I see a lot of people storing their regulators with the hoses very tightly bound. Try and keep the hoses quite loose so that it doesn't create stress on the crimping of the hose, particularly on the first stage side. Another thing as well that I see, please be very, very careful with things like silicone spray. I see a lot of guys taking things like silicone spray and spraying it onto the faceplate of their regulator and buffing it up so that this looks nice and shiny. The problem with that is the silicone spray will go through these little holes here onto the silicone. And because the silicone spray comes from the same family as the silicone diaphragm, guess what happens? They bond. So have you ever seen or felt an inhalation diaphragm, for those of you that have taken regulators apart, where the diaphragm feels feathery, it feels like it's been dipped in flour? Or if you stretch the diaphragm, it takes a minute for the diaphragm to come back to its original position. This is a diaphragm that has had silicone spray on it. So yes, silicone spray is a good idea. It does do some protection, but rather spray the silicone spray onto a rag and then buff onto the faceplate of the regulator. Makes sense. Yeah, those are good daily tips. I hope that answers your question, Miguel.
I think you were pretty clear, and I would like to ask you one thing, because I have my thoughts, but you're the expert, so I would like to ask you one thing about blowing air on the screw of the DIN or into the hole of the A clamp. like when you detach your regulator from the tank,
Yeah.
and then the tank is still wet, the tank valve is still wet, and you blow air inside for drying it. I don't know, because
Don't
I've
do
seen a lot of
it.
people doing it, and for me it's, I think
Okay,
it has
don't do
no
it because,
sense.
okay, what you don't want to do is be taking that high pressure air and forcing the water into that inlet, because that goes directly onto the filter. Let me see if I've got a picture of a filter for you. I'll find one quickly, Andrea. Sorry, man, give me a second. I'll show you what the filter looks like. But it's a little filter that's made out of phosphor bronze balls, and generally it's an extra check from the compressor to make sure that we're getting dry, pure filtered air through to the diver on every breath. Sorry, let me just have a quick look here. I'll show you a
If you don't
picture of
find
a
the picture,
filter.
I can take one filter from here,
Don't stress. You
because
know what? Maybe, guys, I see that the time is actually getting on. We're at 8:30 now, so we've been going for an hour and a half. I don't want to make it too long, but basically, I would not recommend forcing that air, particularly into the inlet, because what you could be doing there is forcing water onto the filter. And as I've said, getting water onto that filter can block the filter, and this can reduce the performance of the first stage. If you are needing to do it, I often hear guys really crack the valve open so that it's very loud. You don't need to do that. You can just open it very, very gently and do it on the actual dust cap side itself, not on the regulator side. Does that make sense?
yeah, it makes sense.
Yeah. Yeah, but not into the regulator itself. Yeah.
Okay, so another question is from Lorenzo Borsatti. When does a diver realize to improve its regulator, moving to a more performing and expensive one? Like, I think he's,
Oh,
yeah.
you know, Lorenzo, it's very, very difficult to ask a born salesman when. Today is the right day, hey? But now. No, in all honesty, with respect to that, it's funny when I look back to the 80s and 90s. It's funny, divers that were starting diving then, the very first item of hard gear that they bought was a regulator. Today, with a younger generation, the first item of hard gear that they buy is a dive computer. Okay, we definitely are in a computer age. My recommendation on regulators, because it is life support, and now that we've looked at interesting information around how many joules I expend breathing 1 liter of gas in, my recommendation to you is buy the best regulator that you can afford. That is what I would do. All regulators today are generally safe regulators, and don't not go diving because you haven't got the highest performing regulator. Rather have the magic of diving. This is the most important thing. But I would definitely spend more money on my regulator than almost any other single item of equipment.
Yeah, I agree.
So I would say
Completely
buy
agree.
the one that you buy, the one that you buy. And if at any point you are starting to consider extended range or a little bit of technical diving or maybe some side mount diving at that particular point where maybe you're doing slightly more advanced diving, this is usually a good time to get a regulator that has a very, very low work of breathing. That would be a good time to do it.
Then would you suggest to buy used?
Andrea, depending on used, when I look at it from the Scubapro perspective, it doesn't make too much sense on the second-hand side because the lifetime warranty is only to the original owner. But having said that, I would rather buy a well-designed second-hand regulator than a badly designed brand new regulator, to be completely honest. Yeah. So again, the best performance that you can afford.
Okay, and another question that I think you already answered uh, plenty is, how much is it important the scuba gear quality if I'm a brand new scuba diver? I think you already said that it's good to have good quality, but go for what you can afford.
Go for what you can afford. Go for the best equipment that you can afford. And as I say, I would almost say that the rank structure of the equipment there should be the diving regulator, then the BCD, then the dive computer. I would say that should be the correct way. I think everyone buys a dive computer first, so they don't ever have to do dive tables again.
Okay, we ended the question. We have just a last question that is from Jacques that says, "Thanks, Steve. When do I get to test it?" I think he's talking about the technical gear release that you're gonna do in July.
Yeah, come and join us in South Africa, Jacques. Or even better, I'll come and join you in Madagascar. Huh?
Yeah, why not?
Oh, good. Dene, I'm in.
Okay, so I think questions are ended. No more questions.
Great stuff.
So I would like just to say that if you enjoyed, I'm sorry for the Facebook ones that had no opportunity, but I'm gonna just post the recorded video. And if you enjoyed, just go and have a look at Sakatia Lodge on Facebook. And if you want to know when the next live stream is on, just check Sakatia Lodge or my YouTube channel, but you're already on it, so if you want, just subscribe. And then we are gonna be live in 2 weeks, right?
Yeah, let's do that. 2 weeks. I'm happy.
2 weeks. So
great stuff.
not next Wednesday, but the Wednesday after. Okay.
Fantastic.
So thank you
Great.
very much, Steve. Thank you.
Thanks, Andrea.
For
Thanks, guys.
being here. Thank you very much, and see you in 2 weeks. Bye.
Fantastic. Go diving.